When we ask, why is the sea salty? We're really diving into the entire history of our planet. To understand, we must go back billions of years to the very birth of Earth. If you like similar educational content, please like, subscribe, and share this video with your friends. Where did the water come from? There are two main theories. Volcanic outgassing. In Earth's early days, constant volcanic eruptions released gases and water vapor from the mantle. As the planet cooled, that vapor condensed into liquid water, creating the first oceans. Cometary and asteroid delivery. Many scientists believe icy comets and water-rich asteroids bombarded Earth during the late heavy bombardment, delivering additional water that filled and deepened the oceans. So Earth's oceans are a mix of deep planetary chemistry and gifts from outer space. Rain, rivers, and erosion. As soon as water began cycling through the atmosphere, rain fell across a barren landscape of rocks. Rainwater is slightly acidic because it absorbs carbon dioxide from the air. Flowing across the land, it dissolved minerals from rocks and carried them into rivers. Over millions of years, these rivers acted like conveyor belts, transporting sodium, calcium, potassium, magnesium, chlorides, sulfates, and carbonates to the sea. Every drop of rain brought tiny amounts of dissolved minerals, which slowly but surely built up in the ocean. The earliest chemistry, at the same time, volcanic gases like hydrogen chloride and sulfur dioxide were dissolving into seawater, adding even more salts. This mixture created a primitive ocean that was already salty long before complex life appeared. Why not lakes? You might wonder, if rivers deliver minerals everywhere, why aren't all lakes salty? The difference is outflow. Most lakes drain into rivers that carry dissolved minerals away. Oceans, however, are basins without escape. Minerals enter, water evaporates, and salts remain. That is why oceans accumulated salt for billions of years, while most freshwater lakes stayed fresh. Only closed basin lakes, like the Dead Sea or Great Salt Lake, become hypersalty because evaporation concentrates their minerals. The endless cycle of erosion, every rainfall, every stream, and every river carries tiny fragments of Earth's crust down into the sea. Rainwater, slightly acidic due to dissolved carbon dioxide, slowly wears away rocks through chemical weathering. Granite, limestone, basalt, all are broken down molecule by molecule. The rivers pick up dissolved ions like sodium, calcium, magnesium, potassium, chloride, and sulfate. These ions flow steadily, year after year, into the oceans. Though the process is invisible in the short term, across millions and billions of years it has delivered staggering amounts of minerals into the sea. Why doesn't the ocean just keep getting saltier? If rivers are always bringing in new salts, shouldn't the oceans be turning into brine by now? The surprising answer is no, because the ocean has a chemical balance system. Salts are added, but they are also removed through various processes. Sedimentation. Some ions combine with other particles and sink to the ocean floor, eventually forming new rocks. Biological use. Organisms like corals, plankton, and shellfish use calcium and carbonate ions to build skeletons and shells. When they die, these structures fall to the seafloor, locking minerals away. Hydrothermal vents, deep-sea volcanic activity circulates seawater through hot rocks, which strip out certain ions and reabsorb them into Earth's crust. This constant give and take keeps the ocean's salt content surprisingly stable at about 3.5%, roughly 35 grams of dissolved salts in every liter of seawater. Different oceans, different salinities. Not every sea or ocean has exactly the same saltiness. The Atlantic Ocean tends to be saltier, around 3.7%, due to high evaporation and limited freshwater input. The Arctic Ocean is less salty, about 3.0%, because it is diluted by melting ice and river inflow. Semi-enclosed seas like the Mediterranean or the Red Sea can become much saltier because of strong evaporation and restricted exchange with open oceans. Why sodium chloride dominates? Although many minerals dissolve in water, the ocean is especially rich in sodium chloride, ordinary table salt. Why? Because sodium and chloride are abundant in Earth's crust. Sodium chloride is highly soluble and difficult to remove from water once dissolved. That's why seawater tastes like the salt on your dinner table. It's the dominant mineral left behind after billions of years of accumulation. Salt and life's origins, perhaps the most profound part. Life began in the salty sea. The chemical soup of ions provided the perfect environment for early biochemical reactions. Even today, our blood plasma and tears carry a salt concentration reminiscent of ancient oceans, a reminder that all of us are, in a sense, children of the sea. Salt lakes, nature's laboratories. While the average ocean salinity is about 3.5%, some lakes on Earth are 10 times saltier. The most famous is the Dead Sea, lying between Israel and Jordan. Its salinity reaches nearly 30%, making it one of the saltiest bodies of water in the world. Why so salty? It's a closed basin. Water flows in but doesn't flow out. The hot, arid climate causes intense evaporation, leaving minerals behind. Over thousands of years, this concentration builds up until the lake becomes a hypersaline pool where almost nothing can live except special microorganisms. Other examples include the Great Salt Lake in Utah and Bolivia's Salar de Uyuni, where massive salt flats form after lakes dry up. Life in salty extremes at first glance, hypersaline environments look dead. Yet they are home to halophiles, microorganisms that thrive in salty conditions. Some produce striking red and pink pigments, giving salt ponds their vivid colors. They adapt by keeping internal salt concentrations equal to the water outside, avoiding dehydration. These life forms are so unusual that astrobiologists study them to imagine how life might survive in the salty brines of Mars or the subsurface oceans of Europa, Jupiter's icy moon. Salt and the climate machine salinity isn't just a side effect of erosion. It plays a crucial role in regulating Earth's climate. Here's why: salt makes water denser. When water evaporates in hot regions, salinity increases and the dense water sinks. In colder regions, when ice forms, salt is left behind, making the surrounding seawater denser and causing it to sink. This sinking of salty, dense water drives the thermohaline circulation, the global conveyor belt of ocean currents that transports heat around the planet. Without this circulation, Europe would be much colder, the tropics hotter, and the Earth's climate far less stable. Changing world climate change is already shifting ocean salinity. In polar regions, melting ice adds fresh water, reducing salinity. In subtropical regions, stronger evaporation is making waters saltier. If these changes disrupt ocean currents like the Gulf Stream, the climate of entire continents could be transformed within decades. That shows how closely the saltiness of the sea is tied to the future of humanity. Salt as a cultural treasure. Beyond science, salt has always had a special place in human culture. Ancient civilizations valued salt so highly it was once used as currency. The word salary comes from salarium, the allowance Roman soldiers received to buy salt. Oceans, with their endless supply, have always been a symbol of abundance, mystery, and survival. Imagining a freshwater ocean, if Earth's oceans were not salty, life as we know it would be unrecognizable. Marine life. Almost every creature in the sea has evolved to live in a 3.5% salt solution. Remove that salt, and most species would die. Fish regulate their internal salt levels through osmosis. Without salt, their cells would swell and burst. Global circulation. Without salinity, ocean water would have far less density variation. The thermohaline conveyor belt, which depends on salty, dense water sinking at the poles, would collapse. That would shut down global ocean currents and radically reshape the climate. Chemistry of Earth. Many reactions in the ocean, from carbon cycling to mineral deposition, depend on salt ions. A freshwater ocean would mean no coral reefs, no shellfish, and no limestone formation. The entire carbon balance of the planet would shift. In short, without salt, Earth might still have oceans, but they would be lifeless basins, unable to support the richness of biology we see today. Salt as a stabilizer of the planet. Salt is more than just a seasoning, it's a planetary regulator. By controlling water density, it keeps ocean currents moving. By providing ions, it fuels the chemistry of life. And by maintaining balance with the atmosphere, it helps regulate Earth's climate. It's no exaggeration to say that salt is one of the foundations of habitability on Earth. The future of salty seas, but this stability is fragile. Human-driven climate change is altering salinity patterns. Melting glaciers pour fresh water into the Arctic, reducing salinity. Rising heat causes stronger evaporation in the tropics, increasing salinity there. These shifts threaten the global ocean conveyor belt. If it weakens or stops, Europe could plunge into an ice age while other regions overheat. The saltiness of the ocean, built up over billions of years, is now being tested by the rapid changes of just a few centuries. Salt and humanity. We are tied to the oceans, not just biologically, but culturally. Salt gave rise to civilizations, fueled trade routes, and shaped history. Today, when we taste salt on our lips after swimming in the sea, we are tasting the story of Earth itself, volcanic gases, ancient rivers, and billions of years of chemistry. Final thought, so why is the sea salty? Because every drop of rain that fell, every river that ran, and every volcano that erupted left behind tiny grains of minerals. Over billions of years, those grains became the salt of the oceans. And that salt is not just a flavor, it's the silent architect of life, climate, and the future of our planet.